Hello, my name is Alejandro Delgado, and this is my presentation on air resistance and its effect on free-fall motion. In most Physics 1 problems, we ignore the effects of air resistance on a moving object in space. However, it is a very important component of the movement of an object to focus on its air resistance. In Arches National Park, a group of daredevils went rope swinging over 150 feet to complete the world's largest rope swing before 2012. We can determine the value of the air resistance by analyzing the movement of bungee jumpers in the world's largest rope swing video, which I'll show later. Some relevant physics principles for this presentation is that the conservation of energy can be described with the following equation, which is the initial potential energy and the initial kinetic energy, plus any work done, which is just energy dissipated or gained throughout the entire process, which will be accounted for with air resistance and drag is equal to the final potential energy and the final kinetic energy. The equation for work is the vector of force dotted with the vector of radius, or the distance that it travels. And the equation for air resistance in this scenario will be F equals negative B times V, where B is just a constant and V is the terminal velocity. And we'll be trying to find the value for the constant B. Some initial observations and data is that the mass of the jumper is 80 kilograms, the length of the rope is 45.72 meters, and the height is 50 meters. This is all gathered from the video, which I'll now show. It's a very short video, but it tells us exactly what we need to know in terms of how fast the person is falling at the end and how high they actually start. When put into Tracker, this is the data I received, and I stopped it at the lowest point of when the person travels, just to make sure that I don't accidentally account for any weird changes in motion due to the angle of the camera. In order to calculate the final velocity, I took the value of the second to last X position and the last X position over time, as well as the second to last Y position and the last Y position over time, to kind of calculate that immediate change in final velocity to get the most approximate estimate to this actual value. And I ended up finding that velocity is equal to 81.32 meters per second, or when it's v squared to get put back into the equation, it's 6612.7508. When I'm calculating for work and for B, I just ended up rearranging the equation here, and as you can see, B ended up being 1552.24. However, there are many sources of error in this video for many reasons. In the actual video, it doesn't actually explain the person's mass size, for example. I just assumed that I just used the average mass size for the average adult in North America, which is 80 kilograms. And this is a pretty good estimate because they're probably not going to be that much different. And because of the angling of the camera, as in, we don't just see like a flat move, movement cycle. The camera's kind of tilted, and this kind of would change some of the dimensions for the X and the Y dimensions. But I tried to fix it so that we wouldn't really get any of those bad results. But the numbers still may be a bit skewed from the tracker. But overall, what does it mean? Because the impact of air resistance, you think that the period of a long rope swing would change. However, it remains just the same. The equation for the period of a rope is T equals 2 pi square root L over G. Because neither velocity, position, or force is a dependent factor for the period of a pendulum, it actually remains the same. Now what happens if we change the system or the fluid that the pendulum is floating through? In this experiment, we are using F equals negative BV because the rope travels through air. However, what if we change the fluid? A more general equation for drag force is Fd is equal to 1/2 the density of a fluid times the terminal velocity squared times the coefficient of drag times the cross section of the person swinging, or the thing swinging. But the important thing here is rho, which is the density of the material that the rope travels through. The more viscous a material is, the stronger the drag force is on it. So for example, if the rope was to travel through peanut butter, it would have a lot of resistance